Good morning. Welcome to today's lesson on the distributive property and combining like terms. So those two things really do go hand in hand here. So we're gonna deal with them together, one at a time. So we'll start out with something called the distributive property. There are a lot of properties in math. That's what we call them when we have a realization about something. We have the associative property, the commutative property, and so on. This is called the distributive property. Well, it's called that because to distribute, maybe you've heard that word before, it means to hand out, pass out, okay, to hand them out to everybody in your row, for example, would be to distribute. And property is, again, what we call a lot of things in math when we want to talk about something very specific. So let's talk about what is the distributive property and why do we want it? What do we do it for? So the distributive property is when we have a parentheses and we kind of want to cheat. That's really the whole crux of it right there. We don't want to follow the rules because the rules say the distributive property that I have to add the parentheses first. That's what order of operations tells us to do. We all use the order of operations because if we all use it, we all get the same answer. That's why we have it, and that's why we call it the order of operations. So the order of operations here is that we would do the parentheses first, and then a number next to a parentheses means to multiply, so we would multiply it, and we would get our answer. Now that's great when we've got simple numbers like 2, 3, and 3. But what's the distributive property and why? Okay, the distributive property here is so we can ignore or maybe just get around the order of operations. Maybe I don't want to add the 2 and the 3 first. Maybe I can't. Maybe it's not a 2 and a 3. Maybe it's got a variable in it. Maybe it's got something that I can't deal with right now. But you know what? I still could deal with the multiplication. So what this allows us to do is to bypass the parentheses part and jump to the multiplication part. So we even get to go past a few other things. So we're kind of cheating around the order of operations here. What we do is we still multiply the number that is outside times everything that's inside. Now everything that was inside we know added up to 5, but we can break it down into the 2 and the 3 because 3 times 2 is 6, and plus 3 times 3 is 9, and 6 plus 9 is in fact 15. So we got the same answer, we get the same result, we just got there a different way. This is why we like the distributive property. It lets us work around the parentheses instead of having to deal with it first. Specifically, its biggest use is when we have something that we can't do all at once because because there's a variable involved. And this is, again, getting to what we're going to be talking about in the next lesson. Okay. Another application, another sort of way to see this is imagine for a moment that we have ourselves two rectangles, right? Side by side together. I know that this is 3. Let's give it make these feet. I know down here this is 2 feet and this is 3 feet. If you look, it's the same sort of situation that we have up here. If I said, what's the area of all of this? You have two options. You could find the area by adding these two numbers together to get the length down here, and that would be 5 feet. And then you would multiply because area equals length times width, so 3 feet times 5 feet. And that would get us our 15 feet squared. But we could also have done it as two separate little fields. This field is 3 times 2. It's a 3 by 2. That's 6 feet squared. And this one would be, this is 3 as well, just like this one. And 3 times 3 is 9 feet squared. And together, those two, again, equal that 15 feet squared. So we had an option. We had two ways we could handle this problem. We could do it with one piece at a time using the distributive property, or We could have done it all as, well, we'll actually do it following sort of the order of operations and do what's inside the parentheses first. But again, this would be one of those applications that we can utilize for the distributive property. Why do we want it? Now let's look at one of those one problems that has where there's a variable and why we absolutely have to have this thing called the distributive property. Because what if, and we would be telling you to simplify, not solve, simplify 3 times, instead of that 2, what if it were a variable? What if it were x? Everything else is the same, now what? I don't know what x plus 3 is, and neither do you, unless I tell you what x is. Unless somebody comes along and says, hey, by the way, x equals 2 or 5 or 100, you don't know what x plus 3 is because you can't. That's the whole point. It's a variable. It's an unknown. But what you can still do is you can multiply it. Think of it like a variable is like money you don't recognize. You know, you go to a foreign country and they hand you the money that is local, and you go, well, how much is this worth? They could hand, you go to some countries, they could hand you 1,000 of their rupiahs, and you go, okay, what's 1,000 rupiah worth? By the way, that's Indonesian money, and it's worth about 6 cents. You go, okay, maybe that's not worth much. But you could, even if you didn't know how much it was worth at the time, you could still multiply it. You could get more of those if they gave you a bill that was 1,000 rupiahs. They could give you another one that was worth 1,000 and another. You could say, I could get 3 of them. I know what 3 times 1,000 rupiahs is. It's 3,000 rupiah. Even if I don't know how much a rupiah is. Okay? So even though I don't know how much x is, I can still multiply it times 3. All right. Plus 3 times 3 again, we know that's 9. Now, I've done what I can. Notice I said simplify, not solve. I don't know what the solution is, but I have done what I can. I have simplified this, what we call a variable expression. Okay, it has it's called an expression because there's no equal sign, and it's a variable expression because it has a variable in it. Okay, not terribly creative, but that's why we call it what it is. And I have actually done some of the math that I can do. Right? I've gotten rid of the parentheses because I did the multiplication that the parentheses was telling me to do. And the other thing that we use this for, why is this something that would matter to us? Well, this is how computers do a lot of their computations. Now, why do I care? Because this is when you're about to enter a keystroke, it's done all these things and then said, now, tell me what x is, and I'll be able to finish this problem. It does as much as it can without actually knowing what the input number is until you give it the input number. So the point here is, this is how computer programming works. This is how computer programs work. They do as much as it can until it gets the input from whoever it is that is typing on the keyboard. Okay, or even from the disk you've put in the drive or the website that you're interacting with. Until it gets the input, it's doing whatever it can calculation-wise until such time as it gets more input. Okay? That is the distributive property. Now you'll notice I draw these little arrows. Okay, these little arrows are there just to remind myself to do that multiplication. Because here's the problem that happens all the time. All the time, all the time. Okay, so we're going to erase this just so I can work a little higher. And I'm going to tell you, this is the mistake that I don't want you to make. It happens way too frequently. So if I said 2 times quantity x plus 4, students, for some reason, always remember to go 2 times x and go 2x. But then, and then you see that plus sign, and they're golden, and they go 2 times 4, and magically it doesn't come out as 8 on the other side. For whatever reason, they forget. Because they see these together, they think multiply, and they see that plus sign, and then it just doesn't come out right. That is why you will always see me draw little arrows. Sometimes people have said they're little rainbows. These are to remind me that I have to multiply that 2 times everything that's in there. Okay, now this is something that you're going to be able to utilize way down the road when you get into multiplying binomials when you're in high school in the 10th grade. You're going to be doing this again with much more complicated things than the numbers 2 and 4 and x. Okay, But here's where you get the groundwork for it. Remind yourself, that's 2 times x, 2x. That is 2 times positive 4, that is positive 8. Okay? I could even do it, if I wanted to, I could do it with, let's go all the way out here. Let's give it a coefficient in front of the variable. Let's give ourselves, let's go crazy. Let's give ourselves 2 variables that are different. Let's give ourselves one more number. Heck, you know what? Let's change that to subtraction. Let's really make this hard on ourselves, because we need to be able to handle anything that comes up with this. So what do we do? This is where I bring in the rainbow, because I want to make sure I remind myself to multiply it times every single number that I've got. So I have 3 times 2x. 3 times 2x is 6x. I have 3 times positive 3y. Well, 3 times positive 3 is positive 9y. One more time, one more rainbow. 3 times negative 1 is negative 3. I had to make sure I multiplied everything inside the parentheses times the number that was outside the parentheses. Okay? And if the number outside the parentheses, I'm going to go one more on you here. What if the number outside the parentheses was negative? How would that change? Well, let's give ourselves an easier one. Okay? One more thing we want to talk about. So we have a negative 2 times a positive 3. A negative times a positive is a negative number. So negative 2 times positive 3 is negative 6. And x is right along for the ride. We go again with our little rainbow. Negative 2 times negative 4. And negative times a negative is a positive. Okay? It's a lot to take in, I know. But that's why we want to draw those arrows. I sometimes like to circle my numbers, especially if they have coefficients that matter, especially negative coefficients, negative signs. Really want to make myself clear. I want to be very careful about how I put every number into the setting. Okay? And that's the distributive property. Now, something that comes along with the distributive property that's almost always right after you're done with the distributive property is this idea of combining like terms. So let's chat about that. Combining like terms. Well, what does that even mean? Well, let's break it down. A term in math is anything. It could be a number, it can be an expression, it could have a variable. So term, that could be things like 3x, 4y, or just the number negative 6. Those are all terms. They're all a variety of terms. Like, meaning alike, right? Two things that are alike, they have the same variable. Okay, it could be x, could be y, could be z, could be x squared. As long as they're all the same, then they are alike. And ones that have no variables, we call them constants. They are automatically alike. We didn't even tell you that. When you were in the first grade and you learned how to add 2 plus 2, nobody told you, by the way, we're adding like terms. But that's what we were doing. We're combining like terms. The terms happen to be constants, and they happen to have no variable. That's what made them a like term. But that's what we're doing. And combining means to put together. Okay? And you'll find we're almost always using addition. In fact, when we're confronted with subtraction, one of the things we might actually do is to change the subtraction into the addition of the opposite, and I'll show you what that looks like in just a second. Well, let's start with a very easy one. You get something that looks like this, 3x plus 2x. That seems pretty straightforward. This is like first grade. Instead of just saying x, what if we'd said 3 apples plus 2 apples, right? Little kid gets it, 5 apples, I understand. Well, for us, we're using something a little more complicated than an apple. We're using an unknown, a variable called x, but it's the same exact principle. 3x plus 2x is 5x. Seems okay to me. Okay. Same thing, what if we did it as 3x minus 2x? Well, that seems also just as simple. 3 minus 2 just gives us 1x. Most of the time we wouldn't write the number 1 as a coefficient, we would just write the letter x. It's just the way we are. Okay, we rarely say 1. We don't even say it in most of the time in our regular conversation. If I ask you what I was holding, you would simply say a pen. You wouldn't say 1 pen. Just we don't feel the need to quantify until we get past 1. So that would be how we could do it. We could have it as 3 minus 2 is 1, or simply x. And these are like terms that we are combining here. Now, what if there was some separation between them? What if we said, how about 3x plus 4y plus 2x? Well, now what? There's still some like terms. The x's are still alike. It doesn't matter how far apart they are in the expression. We can still combine them. Keep the sign of what's in front as part of the number so that you're not adding when you should be subtracting and vice versa. And I'll show you what that looks like in just a second. So still there'd be 3x plus 2x is 5x. And then the 4y is still there as 4y. And that's as good as it's going to get. That is, again, you'll see this later on. It won't say solve. It'll say simplify. Because I don't know what x is, I don't know what y is, but I do know, it's like even if you don't know what the money is. Let's say you didn't know about American money. I could hand you a handful of change and say, please separate this into those things that are called quarters, those things that are called dimes, those things that are called nickels. And you could tell me how many of each we had. You could tell me we have 5 quarters and 4 dimes. You could easily do that. Even if you had no idea how much money that was or what they were worth, you could distinguish between a quarter and a dime. You can distinguish between an x and a y. So you can always combine like terms even if you don't know what the term represents yet. Okay? Now, I was going to say, what if there's a subtraction? What if it was 3x plus 4y minus 2x? Well, again, don't see this as like, sometimes students do this. They go 3x plus and then they leapfrog. This is a positive 3x, this is a positive 4y, and this is a negative 2x. So actually, I'm going to put one line under it. So you can see 3x minus 2x. This is our 1x right here, and then plus 4y. And I know I'm writing down, you've seen me do this enough times, you know what it looks like. Okay, so that is what you're doing. When you're combining like terms, you're looking for this variable that are the same, and you're combining them, and you're ignoring everything in between. So we go 3x, and we just ignore plus 4y. We jump right to minus 2x. Those, with the signs, are the two terms that are like terms. Okay? Now, we're almost done for this. Okay? And if this is something that you can really wrap your mind around. I like to underline my like terms. Sometimes, and I notice I like to put like one line under I'll put one line under the first term, and then one line under all the other ones that are alike. And then I'll put the next term I come to, I'll put 2 lines, and I'll put 2 lines under all the other ones that are like that one, and so on until I've gotten to all the terms that are in there. Usually, for us, we're probably not going to see much more than about 3. Pretty sure 3 is about where we stop. Now, there's no reason why we couldn't have 50 terms. We could, or, we know there's the whole alphabet, right? A through Z. That's an easy 26 terms. And then if we start adding exponents, we can go on forever. But for right now, we're probably going to see, an x, a y, and a constant, an a and a b and a constant. Eventually, we're going to be doing stuff with an a and a b and a c. Okay. But this is what it means to combine like terms. Find 2 terms that are alike, that have the same variable raised to the same exponent, and then you can combine them by whatever means it is to be combined, if they're supposed to be subtracted. And it's only going to be adding or subtracting. We do not combine like terms in any other way. That would be something different. We're talking about combining like terms, that's adding the terms or subtracting the terms. Now, if you don't like subtracting, if maybe that's not to your liking, I said that we were going to go one more thing here. So let me chat about this one. And that is something called, we're going to add the opposite. Let's say that same problem, 3x plus 4y minus 2x. Some reason this is getting you confused. This is getting you keep wanting to go 3x plus 2x instead of 3x minus 2x. Well, if you don't like a subtraction problem, you can change a subtraction problem. You can turn a subtraction problem into addition of the opposite using one of my little favorite tricks here. And you're going to hear me say this a lot in later videos, and maybe when you see me in office hours in class, we're going to put a little cheese on it. And I know you're thinking, what the heck is he talking about? Put a little cheese on it. In Spanish, what do we call cheese? We call cheese queso. Well, for us it's queso. K-S-O. What does that mean? K, keep. We're going to keep this just the way it is. So, subtract. I'm not going to write subtract. Why did I say that? Switch. It was already subtraction. We want to switch it to addition. And O to the opposite. This is now a negative 2x. Now it's clear to me that everything's addition, and I just have a 3x and a negative 2x, which we know is 1x and a plus 4y. But you know what? You'll never find your answer with the number 1 written there, so it only would look like this. Okay? So if you don't like subtraction, get rid of it. Change subtraction to addition of the opposite. You're allowed to change subtraction to addition, and if you needed to, you could go backwards, but you never will. You can also change multiplication to division, or vice versa. You can change division to multiplication. I'm sure you remember that from when you had to divide by fractions by multiplying by the reciprocal. All right, now we're going to tie these two things together, combining like terms and the distributive property. So what happens if we have a problem that looks like this? 3 times x plus 4 minus 1. Added one little teeny little thing there outside the parentheses. Well, parentheses says to do what's inside the, the order of operations tells me to deal with the parentheses, but I don't know what x plus 4 is. So I know I can jump to the distributive property. 3 times x is 3x. 3 times 4 is 12. And now I just bring down the minus 1, and now I have some like terms. Well, 3x, there's no more x's, so that's all I get. But I have positive 12 and negative 1. 12 minus 1 is positive 11. And now I have used the distributive property and combined like terms to come up with a final, and again, only simplified, not an answer. It's not a, I don't know what x equals. I didn't determine that x equals something yet. And we will get to that fairly soon. But for right now, we want to master two skills: combining like terms and using the distributive property. Usually the distributive property leads to combining like terms almost every time. Okay? I hope that helps. That should cover you for today. Hopefully that'll help you in your homework, and I'll see you in office hours.